So welcome to this exercise session. And these exercise sessions will also be on Zoom for those of you who cannot be here physically. And in the beginning, we often do take questions from you about the exercises, or we present some additional theory, which was included in the material for the specific week. In addition, if you guys have questions about the topics from last week or some of the material which we have, this is also the time when we would take up these questions. And then later during these sessions, we will also break in with some kind of questions using a software like Multimeter. I don't know if you're familiar with that. That's totally anonymous. It's just in a way to see if people have gotten basically all the messages about what we are doing. So there are two topics this morning, and I will use something like half an hour on that. One is related with exercise 1, derivatives of matrices, and the other one is related to exercises 2 and 3, how to set up and get started, and what kind of results you should expect to see. Now, you've probably seen a message or an announcement that there was a small typo in exercise 1. I have corrected that one. So feel free to download the latest version. That was simply a transpose which should not have been there. So the topic which we are going to look at first is something which you find by just scrolling down here to the derivatives of matrices and vectors. So this is just a reminder of what we did last week about these derivatives. You can obviously set up everything in terms of the single components, which you put to 0. But then it's very convenient to rewrite everything in terms of a matrix. So what you could think of is to have y as a vector of a specific length. And this vector could be a function of a multidimensional vector x. So you could think of a function which, so y could be a scalar, it could be a vector, it could be, for instance, a gradient, and that could be a function of x, y, and z, the Cartesian coordinates. And the way you would represent the derivative of this question, of this function, is in terms of what's called the Jacobian. So what I'm setting up here defines the way you're going to calculate derivatives. So let's just switch over to the whiteboard so that we have that one immediately. So let's do that. And take a look at these quantities in more detail. So what we are going to have is a function, and this function could be a vector. So let's now say that we have y here, which is a vector of length n. And then we have x, which is another vector of length n. These are just examples, random examples we are setting up. And we are assuming then that y here is now a function of some f of x here. And what we want then are obviously the derivatives. We want dy of d of x. So that means that this is normally ordered using this Jacobian matrix. And this is something you may have seen. Sometimes people cover it, sometimes they don't cover it when they do a multivariable analysis and linear algebra. And often these kind of small technicalities are it's seldom that they would touch upon them in a course in mathematics. Sometimes they do, sometimes they do not. For us, this becomes important because, as we said during the lecture last week and also this week, most of the things which we will do will be represented in terms of matrices and vectors or tensors. And then wrapping our head around this and thinking of the structure becomes very important when we store information. So this means that this object here, we would have something like dy, if we start with 0. So that would be the first derivative, dx0. And then we can order things row-wise for y. So that means that we have a dx1. So every column would then be the x degrees of freedom. So if you have x, y, and z, you would have 3 columns, just to give you an example. And this goes all the way up to the last dy0 of dx n minus 1. And then we go down again. And then we have a dy1, dx0. We have a dy1, dx1. And this goes all the way to dy1 of dx n minus 1. And then we continue all the way down to the last dy, which we call m minus 1. And this is dx0. And finally, we have dy m minus 1 of dx n minus 1. Yeah. Yes, that's just a definition. That's the way we typically would represent the derivatives of this function here. So this function here is actually dy dx. And you can choose whether you want to have the derivative with respect to x or along the rows or along the columns. And the way you define it has a consequence for how you define the output of calculations. So just keep that in mind. When you have opted one way to define your matrix, you should stay with that, because it's easy to mess things up. So this happens when you're setting up matrices of derivatives, and then you're multiplying that with other matrices. And then if you don't sort properly the matrix elements, then you can easily multiply the wrong quantities. Yeah. 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 So we will make a clear distinction. A matrix is a two-dimensional tensor. So normally you use tensors when you go beyond 2 dimensions. So when you talk about a matrix, that is an object which is a two-dimensional object. And this is one of the most common quantities which we are going to deal with. But clearly you can have multi-dimensional matrices, or tensors as we call them. So vectors and matrices are explicitly 1- and 2-dimensional objects, and the most common quantities we encounter. So the reason why I say this is that if you now think of what you have here, so if y is a scalar and x is not, if y is a scalar, that means that in that case, we will only have this row here, right? If y is a scalar and x is a vector. So that means that in that case, the derivative is a 1 times n matrix. So let's just write this down, because if y is a scalar and x a vector, then this dy dx is simply given by dy dx0, and then we'll have dy dx1, and all the way up to dy dx n minus 1. If on the other hand, x is a vector and x is a scalar and y is a vector, so you have a 1-dimensional function, but you can have many components, then this would be, the derivative would just be a m times 1 column. So if x scalar, so we say that in this case here we have a 1 times n vector. If x is a scalar and y a vector of length m, then what we would have is a dy dx is actually given by a dy0 dx, dy1 dx, and all the way down to dy n minus 1 of d of x. And then we say that this is a vector of length n times 1, or a matrix of n times 1. So these are just simple notations which we are going to deal with, okay? Now, when you're calculating derivatives of the vectors and matrices, then what is very convenient to do in the beginning is to break it down in terms of the explicit expressions. So one of the examples which we are going to look at, which we will need if we do that, so just keep in mind this kind of notation here. If we then have now a vector, so let's take an example here. We have a vector y, which is given by a matrix. So remember now that uppercase letters are normally matrices, and lowercase letters, we will normally use those for vectors. And if we don't say anything, if we don't have any subscripts, this could be a vector. Sometimes it's irritating because you have to guess from the context, but in general, we are assuming that these are vectors and matrices. So what we are saying now is that this is a vector of length n, and we say that this is a vector of length m, and this could be a matrix which is simply m times n, okay? Now, what we know then is the following. If we look at a specific component here, so we would have a specific component y of I, where these i's, all i's, they go from 0, 1, 2, up to some n minus 1. This is something which is equal to the specific matrix element. So I have an aij multiplied with x of j. This is the explicit component for y, given in terms of the matrix elements and the vector elements x. So is that something which rings a bell back from linear algebra? So this is often pretty useful to do when you're going to break this down. And there are more examples in the lecture notes. So that means that so the matrix A is just a matrix which we set up like A00, A01, A0. And this is a matrix of dimension which has n columns, so n minus 1. And this goes all the way down to A of m minus 1 of 0. And finally, we have m minus 1 of n minus 1. And then we want the derivative. So what we are going to do now is to look at the specific component. Because if you go back to the Jacobian, if you go back to that one, we are now looking for, let's say, one of these components here, or any of these. So that means that what we want now is a derivative of y, so a specific element in the Jacobian matrix. So we are interested in dx, dy with respect to x of k. So if you're thinking of Cartesian coordinates, x could be the spatial dimensions x, y, and z. So you have three spatial dimensions if you're in 3 dimensions. And then we see that immediately from this specific expression that we pick component k. So that means that this has simply to be equal a, I, k. And this applies for all I, which go from 0, 1, 2, up to n minus 1. And this applies also for all k, which go from 0, 1, 2, up to n minus 1. So that means that the derivative is just given by the component of that matrix. This means again that if we now take dy of d of x, this is simply going to be given by this matrix A. So we would have A00, A01, all the way up to A0, n minus 1. And then we go down here to n minus 1, 0. And then n minus 1, an, not that one. and then it's n minus 1, and which is simply just equal to that matrix A. So that's one example. Now, the other thing you could do now is to take a scalar. So if we are doing the derivative of a scalar and we have a vector x, then we remember now from the definition of the Jacobian that in that specific case, if y is a scalar and x is a vector, then we should simply get this quantity here, okay? And if I want to write that as a column vector, I have to take the transpose. So one thing we could do now is simply to look at a very simple case. So we could now assume, and this we call this example 2 here. So we could look at the inner product. So we could now look at y equal to a vector z of t transposed multiplied with x. And now we are not specifying the given the dimensionality here, but when we write it out, we should do that. So this would simply be given by a sum. This is an inner product now, so it means that we would have a sum which starts from 0 up to some n minus 1. So this is a scalar now. So keep that in mind. So y is a scalar. So this is simply c of I multiplied with x of I. That's the inner product. And we know that that's just a number. And now we would like to have d of y of d of x. That's just one quantity we are looking after. And now we can repeat the same exercise, but now we remember that y is a scalar. So that means that we have to have a row with elements. So it's just an n times n, 1 times n vector. So if we look at that quantity, what we need now is to take the derivative of that one. And we are going to make an assumption that z does not depend on x. This is a very common assumption you will encounter in many of these machine learning algorithms. Like when you look at the mean squared error, the design matrix does not depend on the unknown parameters beta. Okay? So that means that we have an important assumption here which makes life easier, that this one does not depend on x. And now we want this quantity here. We could actually write this out, y, if we now look at d, so this y is a scalar, so we could just pick a component, xk, and we see that this is simply equal to z of k. And this applies when you take the derivative, because we pick a specific component k for x, and that means that we end up with z of k. And this applies for all k from 0, 1, 2, up to n minus 1. And then, since we have opted for this definition, since y is now a scalar, what we have then is simply the following. So that means that dy of d of x has to be equal this vector, which is dy dx0. Is actually, so let's just write it out in another way. So let's just write out the final answer. So this should be z0, z1, all the way up to the n minus 1 component. And this is equal to c of t. Because we have defined the vector z to be the column vector. So there was a small typo in the exercise. There was actually a missing transpose. Okay. Say again. Yeah, no, this is my fault actually, because you can actually look at things, you stare at them, and you think it looks okay. You do copy and paste, and then sorry for that. But you see immediately, if you stick to the definitions you have made, if you interchange the definition of the derivatives in the Jacobian matrix, then you simply have to just interchange your definitions. Okay? So the easiest way is actually to write out the components. Now, many of the quantities which we will take the derivatives of are scalar quantities. The mean squared error is a scalar. It's just a number, right? And that's a product of matrices and vectors. So if you now take a second example, example 3 here, you could think of a new scalar, and let's just call this for alpha, which is given by a vector y of t multiplied with a matrix times a vector x. So we're assuming again that alpha is a scalar, like that. Now, what you could do now is simply to use what you had in example 2 here and redefine the quantity you have here and just define a z of t equal to y of t times a. That's the simplest way you can do this. So, because y of t times a gives you a vector. And that means that what you can do then is actually to rewrite the derivative of d of alpha with respect to x. And now there is an assumption again here that these two quantities, this one and that one, do not depend on x. If they do, then you have to set up the chain rule of derivatives. Okay? So that's just another complication. But the thing now is that what you have is actually something which goes like d of z of t times x of d of x. And if we go back to what we had previously here, this is the same. So this will be the same as z of t, which is the same as y of t times a. Yeah. So alpha is just a scalar. And many of the quantities we will deal with is actually you optimizing a quantity which is just a number. And when you're setting up a neural network, you're calculating the output of the neural network and comparing that with the quantities you want to evaluate. And that is simply a number, a scalar. So that's a very common situation which we encounter. And this is why in the beginning, we just want you to just wrap your heads around these topics, because it's useful to get started with this kind of way, this way of thinking. Now, in the text, in the Jupyter Notebook, you will find more examples. And if you do spot typos or things which are unclear, just send us a message. So these are examples. So if you think of the mean squared error, so your example 4, which is the mean squared error, this is something which we wrote like 1 over n, and we have a y minus x times beta transpose times y minus x times beta. And in that case, we are actually interested, and we call this function for a cost function of beta. And what we want then is the derivative of that quantity. And there is an important assumption then that these two quantities here, y and x, do not depend on beta. Now, and this quantity which you have is a scalar. But when you're taking the derivative of a scalar with respect to beta, because beta now is a vector, if we write it like this, it will contain a beta 0, beta 1 up to beta of p minus 1. So that's a vector of a given number of components, which means that this quantity which you see here, this is a vector. So this quantity here is a vector. Because C is a scalar. And you see that now because here you have the inner product of two vectors. So the thing you need to do here, if you follow the instructions in the lecture notes for this specific week, you will find hints on how to calculate these derivatives. And then also keep in mind that beta of t is equal to beta. I mean, the elements are the same. So you can always choose to represent it like the transpose or as a column vector. I mean, that's up to you, how you want to present it. Yeah, yeah, exactly. What? Yeah, yeah, exactly. That's an important point. In a sense, whether you take the transpose or not is something which depends on how you're going to use it in the equations. Just a small question. Why do we actually call this linear regression? Have you thought of that? So just a small hint. We made a model where we have y tilde, that's the model, which is given by this matrix times beta. So have you thought why we call it linear regression? Yeah, it's a linear dependence on beta. So in the exercises here, if we now move to the next step, so in the exercises, we have used a polynomial, but there's nothing which hinders you to write this y tilde. So let's just look at a specific component. You could have it like beta 0, the intercept, plus beta 1 times sine of xi, plus a beta 2 times the exponential of minus x of I. That would also be linear, but suddenly you have different functions. You don't have a polynomial. So it could happen that you have some insight about the problem which says that the data behave like this. However, if I now were to make this choice, let's say I have beta 0 plus xi times sine of beta 1 plus e to the minus beta 2 times x of I. What would you say about that function? Would that fit with the idea of linear regression? So what's the voice of the people? No, because these are nonlinear functions. Because if you see that immediately, if you Taylor expand sine, it goes like beta to the power of 1, beta to the power of 3, beta to the power of 5, etc. So then you suddenly don't have a linear dependence. So when we say linear dependence, it means that we can have very complicated expressions here, like sine functions, cosine functions, etc. But we have a plain linear dependence in terms of these parameters. That's something, it's just a small kind of triviality, but it's always nice to know why something is called what it is called, right? I cannot tell you why I'm called Morten, because that's probably a name my parents liked. That's another thing. But linear regression at least has some kind of meaning. Okay, so the thing which we want to do next is simply to move over to the way we solve exercises 2 and 3. So in the lecture notes for this week, you will find examples of how you can do it, just to get started. And we are going to use this material when we move into the project as well. So the first project will essentially deal with different types of linear regression and U-fitting functions And eventually we will have some real data which are going to fit as well. So let's switch back, unless you have any questions. So I hope the thing with derivatives is a little bit clearer. Take a look at the notes. Hopefully that can help. And the reason we do it is simply because we want you to get started with thinking about matrices and vectors and their derivatives. So let's move back to the slides. And you're probably seeing that there is more, no, not that one. I wanted the, oops. That's the one I wanted. Just a moment. I didn't find the screen here. Let me just do that one. Sometimes I get lost in all the windows I have. Now you should be able to see it. I don't think it's seen by the people which are online. There we are. Okay, now everybody should be able to see it now. So if we scroll down a little bit here, and you can look at these examples and some other useful relations. And we have also the Hessian matrix. But the idea now is to take a look at the example for the exercises. So the kind of exercise which we wanted to do is an exercise where we have decided what the input looks like. And so we have a random number between 0 and 1. And then we have a function y, which is now a polynomial. And there is some random noise here, as you can see. So we can take away the random noise in the beginning, and this is a very useful test. And in this particular case, I don't know anything about the function, and I'm just guessing that's the 4-order polynomial. This is obviously an overkill. If you add larger and larger polynomials, you may actually end up with results which are not very good. But in this case here, you see the code is pretty simple. We just invert the matrix. This is our design matrix. So in each column here, you have 1, x squared, x cubed, and x to the power of 4. So this is now a, since we have 100 points here, this is 100 times 5 matrix. And that's my design matrix. And I'm keeping the intercept. Next week, we will see how we can get rid of the intercept and not use that one in the fifth. There is material in the slides here, but we will not cover that this week. We will discuss that next week. So in the slides, there's normally more material than we will discuss here, but feel free to take a look at them, because this is background material which we will need when we are discussing the setup of our data. Alternatively, there is a least square with NumPy, which you could use like that. And here you see the fit we make. Then we can calculate the R2 score, or we can calculate the mean squared error. So you can write it yourself, or you can use scikit-learn, which has a functionality for the mean squared error. But this is just how you would do it yourself. And actually what you have here is the entry point to project number 1. So in this specific case, we just run it, and then we continue. And you can see this mean squared, now this R2 score should ideally be equal to 1, because we have a perfect fit here. Alternatively, we can look at the mean squared error, which should be as close to 0 as possible. So this is essentially 0. And you can also do the relative error. That's also a quantity which many people like to look at. Now, the thing which you see immediately now, if you add noise here, So suppose we make it a little bit larger. So let's rerun it. What you will see then is that due to the noise, you will not get 1. This number, the R2 score, can actually be negative as well. And if I calculate the mean squared error, you would then see something which is not something you would be happy about, because you would like to have it as close to 0 as possible. So this means that you have large deviations in your data set. Okay, so this is pretty intuitive, isn't it? So take a look at these examples. This is essentially exercise 2. Now, in exercise 3, we are going to do something different. We are going to split the data in test and training. And the reason for that is that you can fit a model to perfection. So later, when we are going to look at something which is called decision trees, you can actually tune this tree to make a perfect fit to your data. But then if you add new data, you may actually fail miserably in making a prediction. Now, in this kind of cases we have here, these are what we normally call vanilla cases, because it's easy to generate new data. So you could actually now, if you look here, you could think of saying that, okay, this is my input X, and then I would just generate new input and output and use that on the model which I've trained and see if that makes sense. Because you can generate data continuously, easily. You can not even blink before you have a new data set. However, in real data sets, these are often the results of long time experiments. And you may only have a few hundred data. And then when you're training a machine learning model to make predictions, you cannot include all the data, because then you would simply train to perfection and you would have a pretty poor predictive power. So this is the basic philosophy between splitting the data and training and test. Later, we will also discuss how you can make, with these hyperparameters we introduced yesterday in the lecture from ridge regression, you will see that we can also have a so-called validation data set. So that means that you would split the data into train and test. And here, you can write your own function. There is an example below here where you can split the data. That's up to you. But we would recommend using the functionality in scikit-learn. And here we have a scikit-learn, and that includes one function which is called train test split. And when you do that, so here I have the function, the data, again, the same data. I'm making my design matrix. And in this case, you can see that my design matrix is now split into a train part. There's a test part. And that same for the output. There's a Y train and Y test. And here, I simply decide now that my test size consists of 20% of the data. So that means that you leave that in a vault and you don't touch it. So you do the training on 80% of the data, and then you use this one to the model you have fitted to test on the test data and see if you make a good prediction. Okay, so that's a basic philosophy. And this is something you will do again and again. So exercise 3 is about this. And typically we would recommend using these ready-made functions like train test split. As I said, you can make your own. These functions from scikit-learn, which is a very popular machine learning library, but it's a library which does not include many of the deep learning methods. TensorFlow, PyTorch, and other libraries have the deep learning methods. The nice thing is that they all interface with scikit-learn. So all the functionality you have with scikit-learn, you can reuse together with TensorFlow, PyTorch, or other more advanced machine learning libraries. So you will often see textbooks saying machine learning with scikit-learn and TensorFlow, or machine learning with scikit-learn and PyTorch. like the one which we have recommended by Rashka. Okay, so feel free to use it. It makes life easier because writing a function like this, when you've done it once, you've done it for all cases, and you don't get a new insight in writing a new function like that. So these are just background functionalities. In this specific case now, you can see that what we do, so we train, this is what we have in the train data, and this goes into the training, and that gives us the parameters. So then we have X train times beta. So this is the prediction we make now on the training data. Okay? Just to see whether the model does a good job on the training data. Then if you go below here, you see now that I make a prediction where I take my test data and multiply that with the parameter beta. So this is my prediction, which I then want to test against the data which was not included in the training. So hopefully my model is doing a good job. Actually, this is a kind of baby case with a simple polynomial, and you will often get pretty good results with that. So let's just take a look at it, because there is more to the picture here, actually. So let's just run it. And you can see now the training, which we get. So this is the R2, which should be 1, the mean squared error. Sometimes you get a better result on the test, but that can be a random thing. Normally, your test mean squared error is normally better than the one, no, the training one is better than the mean squared error from test. Here we also don't have that many points, but then the thing which you could do now, so I had a functionality here. Where did I put that function? Yeah, this is something which is now relevant for exercise number 2 here. And in this specific case now, I'm taking a new function, which is a function which is now given by an exponential of e to the minus x squared. This is in a way a preparation for the project, which comes next week. So this is now a little bit more complicated function I want to fit. So instead of just a simple polynomial. So you can actually, if you don't like the cases we suggest, you can just change it to other functions which you want to try. So let's do one thing now. And let's just reduce the number of data, because the results will depend on how much data you plug in. So let's take a look here. So let's fit up to a 4th order polynomial. Let's say max degree here. 0 is the first one, so I have 5 points. So 0, 1, 2, 3, 4. So I'm doing a 4th order polynomial here. And let's see what we get when we apply this fitting here. And what we are plotting now is, so this is actually discrete values. So this is the 1st order polynomial. This is my training error. This is the 2nd order polynomial. And you see that the training error goes down as I increase the order of the polynomial. And that sounds reasonable because after all, I have an exponential here, right? So the more terms in the polynomial, the better the fit should be. Does that sound reasonable? Yeah. And in this case here, we could also take away the noise. Just let's take away the noise in the beginning, because sometimes that gives us some clutter here. So let's rerun it, and you will see something like this. So this is the result with a polynomial up to degree 4. And you see also that the test case gives a larger error, and that is a pretty common situation. However, everything you see is a result of the number of data and the polynomial approximation. So let's now just change the polynomial degree to, let's say, 14 and rerun it. Now, in this particular case, you see now that the test error just blows up. So this is a typical case of where we are running into overfitting. So we have done a pretty good job in the training case, but the model we have made doesn't do a good job on data which was not included in the training. So we are coming back to how we can analyze and get a signal of overfitting. But this is a very clear signal that the model we have trained is okay up to some degree of the polynomial with the data points we have. So let's now assume that somebody gives you much more data. And let's see if this changes. So let's just change this to 500. Aha, this looks much better. So the results you get will always depend on the approximation you make and the amount of data you have. Essentially, these methods for supervised learning, irrespective of whether we do neural networks, regression, or gradient boosting, or any of the methods which exist, they will always be data greedy methods. So the more data you have, the better the fit you normally make. However, even in this case, if we have all this data, it could happen, suppose now we go to a 20-fold, or let's say a 30-fold polynomial. Because, you know, we have an exponential here, and we have in principle a polynomial of very high degree. Still here you see that the test case is a little bit higher. And the error is still not zero. So there's still room for improvements here. And this is a typical quality of the results which you will get. And with a given data set, this is what you have to live with. And it's you who has to make the critical analysis on when you would stop here. So suppose now that the test error is close to the training error, like here, or you reach a bottom here, then you would say that, okay, I don't need to go to a 30-fold polynomial. I can just use a 10-fold polynomial. And that does a pretty good job for this case. Remember that if you have a 30-fold polynomial, it takes many more cycles to calculate a value for the function. So it's again you who has to strike a balance between accuracy of the model and the amount of CPU cycles you want to use. So at the end point, it's actually us who have to make a decision. So this was, if you look at this material here, this is material which is relevant for the solution and discussion of these exercises. And in the coming weeks, we will look a little bit more deeper on how we can analyze, test, and train errors. This is something which leads to a concept which is called the bias-variance trade-off, and somebody may have heard of that one. It's a kind of holy grail in testing models. Keep also in mind that when you look at textbooks, all the curves are nice and smooth. Whereas when you run calculations here with few data sets, as you saw here, you will actually get something which looks pretty choppy or something like this. So again, this is a case where the test error blows up. You can see here, this is 10 to the 12th. So that means that your model with a 30-fold polynomial is not something you would use on data which was not included in the training. Okay, so this is a kind of a bird's view on what is coming, and just get some practice with setting up the functions in train, test, split data, and then play around with different number of points for the data and the approximation which you make. That is your model. So they will change from model to model and amount of data you have. So don't be surprised if you get different results with another set of data. It's simply because all the methods are data greedy. The more, the better.